All right, class, we're going to continue our discussion of chemical kinetics and rate laws by talking about something called, or developing something called, the integrated rate law that is different from the differential rate law we just learned. Now, the differential rate law, as I think I mentioned before when we talked about differential rate law being based on concentration, we said that there was another form of the rate law that's going to be focused on time. In other words, in a sense, how much of the reactant is left, what concentration of reactant is left over time. This is it. We're going to be mainly focusing on time. Although what we're going to do is we're going to start by taking this differential rate law that we learned about before, where you would have the rate law constant times the concentration of a substance, the reactant, to the order, the power of the order. And we're going to set that equal to the rate that we learned about in the very first lesson in chemical kinetics, which is that you can always calculate the rate of any reaction experimentally by taking the change in concentration over the change in time, and we're going to set them to be equal to another because this is the rate and this is also the rate, and they're going to be equal to one another. In this, because we are going to be talking about concentration over time, we're going to differentiate between two concentrations. The concentration that we call the initial concentration, and that's going to be designated by A0, or let's say that it's chlorine. It would be the concentration of chlorine 0. In other words, the concentration of chlorine at time 0, the initial concentration. And we will talk about the concentration at some point down the road, at some point in time, and that's going to be known as the concentration of A, and that will be, again, the concentration, let's say after 10 seconds, 20 seconds, 30 seconds, somewhere down the road after the reaction has been going on for a while. And again, in this example, you would say, oh, this would be the concentration of chlorine left after a certain amount of time has elapsed. Now, the way we're going to develop this is we're going to look at the three common orders that we learned about for reaction orders. That is first order, second order, and 0th order. Those three orders of reaction that we learned about before. And we will individually derive the integrated rate law that these three different orders of reaction would follow. The first one we're going to look at is first order reactions. Now, the first order reaction, we are going to start with what we started with before. Again, that we're going to take the rate written in differential rate law form, and we're going to equate that to the rate that you would determine experimentally. And you guys, if you look at this graph on the right-hand side, this is a typical graph of the concentration of A, let's say, versus time. You see that graph should not be unfamiliar to you. We've seen that several times already, a graph like that. So we're going to start like this. And then what we're going to do is we're going to rearrange this. We're going to set these two guys equal to one another. And then we're going to rearrange the equation so that we would have the change in concentration of A over the concentration of A is going to equal the negative rate law constant times the change in time. And then we are going to, quote, do an integration, unquote. It is a data transformation that's done, and we don't need to know the details of it. And when we do that, we end up with this equation. All right. Now notice that we don't have the change in concentration anymore. The numerator is now the natural log of the concentration of A over the initial concentration of A, and that's going to equal negative KT. So there's a sort of a data transformation that we do that gives this equation. And if we rearrange this equation, in other words, you know that the natural log of A over the natural log of A0 would also be the natural log of A minus the natural log of A0 due to the law of logarithms. Okay, we're going to rearrange this equation, and what we end up with is this. We end up with the natural log of A being equal to negative kt plus the natural log of A. Again, we just take this this minus the natural log of A0, and we're going to put it on the right-hand side. All right. So if we look at this equation, and I just recopied the equation here at the top of this slide, the natural log of A is equal to the negative kt plus natural log of A. This actually follows a y equals mx plus b format. This should be a linear straight line. Okay, that if you plot the natural log of the concentration of A at some time down the road, if you plot that versus time, you should get a linear graph if the reaction is first order. So again, even though if you plot the concentration of A versus time, you get the typical curve, this kind of curved line that you would see. If you plot the natural log of A, let's say versus time, you would get a straight line, and the y-intercept would be the natural log of the initial concentration. Also, the slope of this graph, if you determine the slope of this graph, you can find the value for the rate law constant. Okay, now we're going to look at second order. Let's derive the integrated rate law for the second order. Again, you don't really need to know this derivation. I'm just showing it to you so that, just that it does come from somewhere. We don't pull it out of thin air. All right, well, if it's second order, then the differential rate law form would be k times A squared, concentration of A squared. And again, that's always going to be equal to the rate that you could determine experimentally by taking the change in the concentration over time. Again, we'll rearrange that equation so that the concentrations are all on one side. Again, we do this data transformation, and what we end up with is this equation. We end up with 1 over the concentration of A equals kt times 1 over the initial concentration of A. Again, once we do this transformation, we notice that this equation, once again, follows a straight line format. This would be your y, 1 over the concentration of A. M would be, again, the slope of this linear curve is going to be the rate law constant. The x value is going to be time, and the y-intercept will be 1 over the initial concentration. So again, even though the initial graph, and I know I didn't show up here, the initial graph of concentration versus time would look something like this, right? The typical curve of concentration versus time. If we plot the inverse of the concentration versus time, we will get a straight line graph, and again, the y-intercept would be the 1 over the initial concentration. The slope will be the value of the rate law constant. Okay, finally, we're going to look at zero order reactions. We're going to derive the integrated rate law for zero order reactions. Remember, this is rare, but in this case, the rate is independent of concentration, okay? And so the rate that you could calculate experimentally will be equal to just k times the concentration to the 0 power, or k. So that's what we're going to start with. We're going to start with this right here. Again, we do that integration, that data transformation, and we get this equation. The concentration of A equals negative kt plus the initial concentration of A. So the concentration at any time down the road that's the equation it's going to follow. Once again, this follows a linear equation pattern. And it turns out that the graph of the concentration of A versus time will be linear, and the y-intercept will be the initial concentration of A. Once again, the slope of this graph will be negative rate law the negative value of the rate law constant. And the graph here on the right just kind of shows you how this would compare to a first order reactions typical curve. Now I get it. That seemed like a whole lot, right? So how would we typically kind of run through one of these analyses in a typical, for a typical reaction like the one you see here, right? So the rate of this reaction above was studied at a certain temperature. And what we did was we monitored the concentration of one reactant, O, over time, and we found this. Now, what we're going to do then is we're going to do we're going to look at two data transformations. We're going to take the original data of concentration versus time. We're going to take the natural log of those. Then we're going to take the inverse of those numbers, okay? And if you kind of remember what we talked about linear, if we plot concentration versus time, let's say we plot concentration versus time. I realize this is small. And we plot that and we get a straight line. Well then, wait a minute. Concentration versus time, that plot being linear means that it would be a zero order reaction. Let's say we plot the log of the concentration versus time. If we plot the log of the concentration versus time, and that graph turns out to be linear, well, then it's a first order reaction. If we plot 1 over the concentration versus time, and that graph turns out to be linear, well, then we know that it was a second order reaction with respect to oxygen. So in a way, what we're going to do is we're going to take the data of concentration versus time, and notice time is involved here. Oops, went too far. Time is involved. And we're going to see which of the three common orders that reaction data follows. In other words, which graph will be linear. Again, if the graph of concentration versus time is linear, then we know that it's a zero order reaction. If the graph of the natural log of the concentration versus time is linear, and the other graphs won't be linear, then it would be a first order reaction. If we plot the concentration, 1 over the concentration of the reactant versus time, and that graph is linear, the other two graphs won't be linear. If this graph is linear, these two graphs will not be, okay? Then we know that the reaction is second order with respect to O. So in a way, you're looking to see, you don't know what the order is ahead of time. What you're looking to see here is which one of the three common orders does the data of concentration versus time fit. And whichever one it fits, then that's how we know what order it really is. Okay, to give you a quick example of how this would look, or how the analysis might look, let's look at this set of three graphs here. Let's say that this is, I don't have the equation on this image, but NO2 is the reactant. Okay, you can tell that because we're plotting, in this case, the concentration of NO2 versus time. And we get this graph that you see here, this purple graph, and that for this reaction, whatever the reaction is, this decomposition of NO2, that is not a straight line. So for this particular reaction, we plotted the concentration of NO2 versus time, and it was not a straight line. It was this purple data set that you see. So it's not zero order. If it were zero order, the graph of concentration versus time would be linear. Let's look at the middle graph. For the same data set where we monitored the concentration over time, we plotted the natural log. On the y-axis, natural log versus time. And when we did that, it was also not a straight line. All right? So what we would say is we would know that this reaction was not first order with respect to NO2. Finally, we plotted the inverse of the concentration of NO2 that we tracked, that inverse of the concentration versus time. And we notice that that is a straight line. So what we know now is that because the graph of the inverse of the concentration of NO2 versus time was linear, we could identify this decomposition of NO2 reaction as second order with respect to NO2. So what we did was we plotted concentration versus time, natural log of concentration versus time, inverse of the concentration versus time. We looked for which of those three graphs was linear. Those three graphs that were linear allow us to identify the order, whichever one. So now we know it's second order with respect to NO2. And also the slope of this line that you see of 1 over the concentration of NO2 versus time, the slope of that line will be the value for K, the rate law constant. Let's look at another example. Here I have the concentration of A plotted versus time. We have the natural log of the concentration of A plotted versus time. And we have the inverse of the concentration of A plotted versus time. When I look at these three graphs based on some data that we collected of the concentration of A versus time, we notice that the first graph, concentration of A versus time, is not linear, so it's not a zero order reaction. We look at the inverse of the concentration of A versus time, and we notice the inverse of the concentration versus time graph is also not linear, so we know that this is not a second order reaction. When we look at the natural log of A, though, plotted versus time, we look at that graph, we see that is linear. And that means that identifies this reaction as a first order reaction with respect to A. And again, the slope of this line would be negative K, because again, you see it's a negative slope. And so the way this graphic shows it, the negative slope is K, but the slope of this line would be the negative value for the rate law constant for the reaction. Lastly, let's look at how a zero order reaction would look. Again, we take some data of the concentration of A versus time. We plot concentration of A versus time, the natural log of the concentration of A versus time, and the inverse of the concentration of A versus time. We notice that in this example, the graph of the concentration of A versus time is linear, which identifies this as a zero order reaction. Also, look at the natural log graph and the inverse graph. Neither of those is linear. So again, the fact that the concentration of A versus time graph is linear, it identifies this as a zero order reaction. And again, the slope of the line would be the negative value of K. Okay, let's look at one last example. So here is a data set that I looked up online, and it's for this decomposition of hydrogen peroxide reaction that you see right at kind of near the top of this page. So over time, they monitored the concentration of H2O2. So this is the way a typical integrated rate law data set appears. There's concentration versus time. Now, contrast this to the way the data set looks like when you're doing a differential rate law problem. There are no time in seconds. Remember, what you have is a list of concentrations, and you have the rates for those concentrations in that kind of data set. in an integrated rate law problem data set, you have concentrations versus time. So what we would need to do is take this concentration data and kind of create a grid next to it. And I can't write on this because this is a website. My pen thing doesn't write on this. We would take the natural log of hydrogen peroxide and write that right next to these numbers. Then we take the inverse of the concentration of hydrogen peroxide. And then we would graph those three data sets independently. So let's look at the results of the three graphs once we did that data. Once we took the natural log of hydrogen peroxide concentration over time and the inverse concentration versus time and prepared three graphs. So when we plot the concentration of H2O2 versus time, we see the typical curved graph. Since the plot of hydrogen peroxide concentration versus time is not a linear graph, we know it's not zero order. Now we're plotting the natural log of the concentration of H2O2 versus time. That graph looks linear. This identifies this as a first order kinetics, or a first order reaction with respect to H2O2. And once again, the slope of this line here would be the negative value of x. So it would be negative k. Well, just for completeness, let's look at what the graph of the inverse of the concentration versus time looked like. And again, it is a curve. So we know this isn't a second order reaction. So let's look at the text at the bottom. It says, since the plot of the natural log of H2O2 versus time is the linear one, we know that the reaction order is first order, with respect to H2O2. This is what the differential rate law would look like, but the integrated rate law would look like this, right at the top of the page. So although the differential rate law would look like, would be the rate equals K times the concentration of H2O2 to the first power. If we write this in integrated rate law form, we would write it as, we know that the natural log of H2O2 equals negative KT plus the natural log of the initial concentration of H2O2. And then you can see that if you know the initial concentration and you know at some time frame down the road, you could actually calculate what the concentration of H2O2 would be. So let's say at 10 seconds, 30 seconds, 100 seconds, 1,000 seconds. By plugging in the initial natural log of the initial concentration, whatever the time value is, the K value comes from the slope of the line of the natural log versus time. And you can then calculate what in this case actually would be the natural log of the hydrogen peroxide concentration times T, and then you can do e to the whatever that is to get the concentration. To wrap this up, we're going to ignore the last part of the slide that talks about half-life. That will be the subject of another lesson. Let's look at a little sort of a summary of how these rate laws would look. Okay, so if I have a zero order reaction, the differential rate law would look like this. The rate would equal to K. Written in integrated rate law form would be the concentration of A equals negative KT plus the initial concentration of A. The plot that would be a straight line plot that would identify it as a zero order reaction would be the concentration of A versus time. And the slope of that line of concentration versus time, that straight line, if it were zero order, would be negative K. Okay, how about first order? We know a first order differential rate law would take this form, where the order is 1. If it were written in integrated rate law form, though, if you were interested in following this reaction over time and not wanting to know the rate for any concentration, but if you wanted to know the concentration after a certain time frame had elapsed, then you would write this rate law here, not that rate law, but you would write the first order rate law if you were interested in what concentration would be remaining over time, you would write it in integrated rate law form, which is the natural log of A equals negative KT plus the natural log of the initial concentration of A. Once again, the graph that would need to be linear to identify it as a first order reaction would be the natural log of A versus time. And if that were linear, then that makes it a first order. The integrated rate law equation would have this form. The differential rate law equation would have this form above. And the slope of this of the straight line would be the negative value of K. If a reaction is second order, its differential rate law would look like that. The integrated rate law would look like this. Inverse of the concentration of A equals KT plus 1 over the initial concentration of A. Again, to identify it like as a second order reaction, if you're not using the method of initial rates, if you're using a data set of concentration versus time, and the plot of the inverse of concentration of A versus time is linear, then you know that it's a second order reaction. So if I plot the inverse of the concentration versus time, and that's the linear graph, sorry, it'll always have a positive slope. Sorry, this graph will have a positive slope. Then you know it's second order, and the slope of this line is K. Again, I realize that was a lot to take in, but I think what you really need to do then to kind of maybe understand this is to look at some sample problems. And of course, as always, there will be a worksheet that goes along with this. In fact, there are 2 worksheets that go along with integrated rate laws that we'll ultimately get to. So hopefully you'll understand it much better after that. So signing off on integrated rate laws.